Okay, so in the last video we talked about a lot of different things. We talked about accuracy and precision. We talked about systematic and random errors. We also talked about how those things are linked. How when you talk about the accuracy of a set of data, you're basically talking about how far away the average of that set of data is from the accepted value, and how that can be a measurement of systematic error. Whereas precision or lack of precision can be caused by random errors, which are more likely to be too high as they are to be too low, and can be reduced through averaging more data points. And then finally, we talked about calculating the uncertainty in a data set using the half-range method. Make sure you understand the difference between using the half-range method to find the uncertainty in an average value and the individual uncertainties usually caused by the measuring device itself. Okay, so those are two different things. Typically, if you were doing like an IA or an experiment, you would just go with whichever of those two was the higher of the two. Okay, so in this last video, we're going to talk about what's called the propagation of uncertainties through calculations. And basically what that means, propagation of uncertainties just refers to the fact how, if you have different measurements and each measurement has its own uncertainties, what happens when you have to do calculations with those measurements? What happens as far as like combining uncertainties when you use like an equation with measured values? Okay, so this is one of the more challenging parts of this first unit. It's still not super difficult. We'll do much more challenging things throughout the school year. But as far as this unit goes, you do need to make sure that you are aware of the rules concerning uncertainty calculations. Okay, so we're going to start off by talking about a type of problem which you might have seen before in chemistry. Okay, and so let's say we have a situation in chemistry where you measure the mass of a beaker that has some copper in it, and then later on you measure the mass of the beaker just by itself. Okay, now the reason you might want to do that, of course, is theoretically, if you subtract those two values, that should tell you the mass of the copper by itself. Okay, so here we have measurements. The mass of the beaker plus copper is measured to be 123.4 grams plus or minus 0.1 grams, and the measurement of the mass of the beaker by itself is 113.8 plus or minus 0.1 grams. Okay, both of these have the same uncertainty, most likely because they were measured using the same measuring device. Now we know how to get the mass of the copper, that is, just subtract these two values, but the question is what happens to the uncertainty? Okay, so if we subtract these two values, we get 9.6, but that would be plus or minus what? Okay, so think about that for a second. What do you think would happen to the uncertainty? Do you think it would stay at plus or minus 0.1? Do you think that the uncertainty would increase to a higher number, or maybe decrease to a lower number? Okay, so what do you think about that? Okay, so the actual answer to the question is that the uncertainty in the mass of the copper is actually going to be plus or minus 0.2 grams. So actually the overall uncertainty is going to increase. In fact, the way we got plus or minus 0.2 grams is by adding those two uncertainties right there, 0.1 plus 0.1. Okay, now it wouldn't make sense to subtract uncertainties, because if we subtracted these two uncertainties, we would get plus or minus 0, which means no uncertainty, which doesn't make any sense at all. And if you think back to the video we watched with Walter Lewin, when he was measuring the student, when the student was lying down and standing up, when he did those measurements, you might not have noticed at the time, but he actually did a similar type of thing, where he was adding the uncertainties in the values of the heights. Okay, so why does this work? Well, you can think of it like this. The uncertainty in the mass of the beaker was 123.4 plus or minus 0.1 grams, which means that the highest possible mass that the beaker could have, given that uncertainty, would be 123.5 grams. Okay, that would be assuming the very highest outcome for that mass. Let me write that down. So this was the mass of the beaker plus the copper. Okay, likewise, the lowest possible mass that the beaker could have by itself, remember the beaker was given a measurement of 113.8 plus or minus 0.1 grams. Okay, and so the lowest possible value for that would be 113.7. Okay, and so the reason I'm looking at the highest top value and the lowest bottom value is because that would give me the greatest possible difference between those two measurements. Okay, and if you were to subtract those two measurements, you would get 9.8 grams. In other words, we came up with 9.6 grams, but it could have been as high as 9.8. And likewise, if you looked at the smallest possible value for the mass of the beaker plus copper, that would be 123.3 grams, assuming you were on the very low end of this top measurement. And if you looked at the high end of the mass of the beaker by itself, that would be 113.9, and if you subtract those two, you would get 9.4 grams. In other words, looking at the extreme values, the mass of the copper by itself has to be between 9.4 and 9.8 grams. Okay, and so that would be 9.6 plus or minus 0.2 grams to give us that range. And so that does, in fact, work if you look at it like that. Okay, and so hopefully what you've seen from this is that in situations where we are subtracting, and in fact in situations when we're adding values, we can come up with a rule to follow as far as dealing with the uncertainties. Okay, and so here's the rule. The rule is on this slide. Okay, and what it says is if y equals a plus or minus b, then delta y equals delta a plus delta b. Okay, so you might ask, what the heck does that mean? What is this y and a and plus or minus and delta and all that? Okay, so basically what this is saying is that if you are either adding or subtracting, so let's say a and b are measured values. Okay, so if you're adding or subtracting any two measured values, delta y, that is the uncertainty in the sum, would be, what is delta a? Okay, well delta a is the absolute uncertainty in A. And likewise, delta B is the absolute uncertainty in B. And so what this slide is saying, and you should add it to your notes, is that in order to find the uncertainty in a sum or a difference, you add the absolute uncertainties. Okay? In other words, when you add or subtract two quantities, you add their absolute uncertainties. Okay, and so that is the first rule for uncertainty calculations that we're going to see. Okay, and I know this is kind of a confusing way to write this, but I'm showing you the way it's written in the IB Physics Data Booklet, so you're familiar with that. Okay, so I'm going to go to the next slide in just a second, make sure you get this down. Okay, and then this is just basically the same slide. Okay, so when you add or subtract quantities, you add the absolute uncertainties in those quantities. Okay, so delta A is the uncertainty in A, and delta B is the uncertainty in B. Okay, so in the example that we just did, we were not adding, but we were subtracting two masses. Okay, and so because we were subtracting two masses, we added their absolute uncertainties. Okay, so in other words, in the example we did with the beaker and the copper, A would have been the mass of the beaker plus the copper, and then B would have been the mass of just the beaker by itself. And delta A and delta B would have both been 0.1 grams, just the absolute uncertainties in those values. Okay, so let's take a look at an example of this. Okay, so we have a rope ladder, as you can see, and the length of the rope ladder is measured to be 9.51 plus or minus 0.15 meters. I'm just going to write this down. This is the length of the rope ladder, plus or minus 0.15 meters, and it's hung from a roof that is 12.56 plus or minus 0.7 meters above the ground. So this is the length of the ladder. I guess I don't need that. Okay, so L is the length of the ladder, and then the height of the roof is 12.56 plus or minus 0.7 meters. By the way, notice how the number of decimal places in each of these matches correctly. Okay, 2 decimal places, 2 decimal places. Okay, and then it says how far is the bottom of the ladder from the ground. Okay, well, of course we would find this is by subtracting, right? Because, well, I can maybe try to draw a picture here. Okay, but if the roof is 12.56 meters and there's a rope ladder, okay, sorry for my bad drawing, that is only 9.51 meters, in order to find the gap between the ground and the bottom of the ladder, right, you would just subtract those two. Okay, and so if we subtract these two, we should get 3.05. And remember, the rule is that when you add or subtract, you add the absolute uncertainties. Okay, and so we subtracted these two values, and the uncertainty would be 0.07 plus 0.15. And so we would write plus or minus 0.22 meters. Okay, so when you add or subtract, you add the absolute uncertainties. Okay, now, as we'll say later, technically what you should do is when dealing with absolute uncertainties, you should technically round to 1 sig fig. Okay, and so if you were to round the absolute uncertainty to 1 sig fig, just because the IB tends to say that you shouldn't have more than 1 sig fig in absolute uncertainties, but if you were to round 0.22 to 1 sig fig, that would round up to 0.3 meters. And then the problem with that is that, remember, the number of decimal places has to match, and now it doesn't. Okay, and so what you would end up writing is 3.1 plus or minus 0.3 meters. I don't know why I wrote it on the blue background. 3.1 plus or minus 0.3 meters. Okay, so because we subtracted, we added the absolute uncertainties. And then, as we'll see later, there's a rule that says absolute uncertainty should only have 1 sig fig. Okay, so we rounded to 1 sig fig, and then we rounded the measured value to match decimal places. Okay, so let's go on and do some more examples. All right, so what happens if you multiply or divide? Okay, now the rule when you multiply or divide, as far as uncertainties go, is basically to find the uncertainty in a product or quotient, you add the percent uncertainties. Now this says that you can add the percent or fractional uncertainties, but remember, I don't really like fractional uncertainty, and so we're only going to do this with percent uncertainties. If you read what it says in this box, this is just a really complicated way of saying what I just said. Okay, when you either multiply or divide, then the uncertainty in the total value you get by just adding the percent or fractional uncertainties. Okay, so delta A over A would be the fractional uncertainty. The percent uncertainty would be delta A over A times 100. Okay, and so on and so forth. Okay, so again, the rule is when you are multiplying or dividing, you add the percent uncertainties. Okay, let me say that one more time so you make sure to add that to your notes. When you multiply or divide quantities, you add their percent uncertainties. So, let's do a simple example. It says a car travels 64.7 plus or minus 0.5 meters in 8.65 plus or minus 0.5 seconds. What is its speed? We will talk more about what speed is later on, but for now, let's rely on your middle school knowledge of speed. Okay, so let's say you probably have seen this before. Speed is distance over time. That is a gross oversimplification, but let's go with it for now. Okay, so let's say we know the distance and we know the time, and we're asked to find the speed. Of course, we can easily divide 64.7 over 8.65. Okay, and if we do that, let me just type that into my calculator. Okay, so 64.7 divided by 8.65, we get that the speed is 7.48, and that's meters per second. But what about the uncertainties? Well, remember, the rule is that when you multiply or divide, you add the percent uncertainties. Now, we have a problem, because if you look, we don't have percent uncertainties. Remember, absolute uncertainties always has the same unit as what you're measuring. Percent uncertainties, well, has a percent symbol. Okay, so we don't actually have the percent uncertainties to add them. Okay, so before we can do anything else, we need to convert these values to percent uncertainties. Okay, so the distance would be 64.7 plus or minus, and then we would do 0.5 over 64.7 times 100. Okay, so 0.5 over 64.7 times 100, we would get 0.77%. And then if we do the same thing with the time, again, all I'm doing is converting from absolute to percent uncertainty, which you should easily be able to do. That would be 0.05 over 8.65 times 100. Okay, so that would be 8.65, 0.05 divided by 8.65 times 100. Okay, so that would be 8.65 plus or minus 0.58%. And so my speed, which I got by dividing, would be 7.48 plus or minus the percent uncertainty in the distance plus the percent uncertainty in the time. And so now that I found the percent uncertainty, I would write plus or minus 1.35%. Percent uncertainty does not need to be rounded to 1 sig fig. That's only absolute uncertainty. Okay, so notice you cannot oversimplify the rule. You can't be like, oh, I'm dividing, so I should add the uncertainty. No, you need to know that you're adding the percent uncertainty, which means if you're given the percent uncertainty, great. All you have to do is add the two. If you're given absolute uncertainty, then you would need to calculate the absolute uncertainty first. Okay, so pause there and make sure you add that to your notes. Okay, so I'm going to erase this. Okay, and here is the summary of the uncertainty calculation guidelines. As long as you follow these guidelines, you will be perfectly fine. Okay, people that get stuck on uncertainty calculations is because they don't follow these guidelines. Okay, so here are the guidelines. When you add or subtract two or more quantities, you add their absolute uncertainties. Again, if you don't have the absolute uncertainties, then you would need to convert from percent back to absolute uncertainty. Okay, number 2, when you multiply or divide two quantities, you add the fractional or percent uncertainty. Okay, you can do fractional if you want. I'm always going to do that in percent. Okay, there's nothing you can do in fractional that you can't do in percent, and I think percent makes more sense, so I'm going to do that. Number 3, your absolute uncertainty should, when possible, be rounded to one significant figure. Okay, that's more of an IB rule than anything. And then, most critically, your absolute uncertainty and your measured value must have the same number of decimal places. And we've spent a lot of time talking about the reason for that, because your last digit is the uncertain one, and so your uncertainty has to be in that same decimal place. Okay, so please make sure you add this to your notes. Okay, put a giant box around it if you want. And this is given to you in the IB data booklet as long as you know how to read it. Okay, this is what it would look like in the data booklet. Okay, so now let's do a few quick examples and then we'll finish up this video. Okay, so it says the power dissipated in a resistor of resistance R carrying a current I is equal to I squared R. The value of I has an uncertainty of plus or minus 2%, and the value of R has an uncertainty of plus or minus 10%. The value of the uncertainty in the calculated power dissipation is what? Okay, so you probably have no clue what that means by power dissipation. You probably have no clue what, all these other words mean, resistance, current, whatever. Okay, that doesn't matter. All you need to do uncertainty calculations is some type of equation. Okay, so here's the equation. Okay, see if you can figure this out on your own. What is the uncertainty in P, given what you know about the uncertainties in I and R and the uncertainty guidelines that we've been talking about? Okay, so the correct answer to this question is actually C. And the reason it's C is because I squared times R is the same as I times R. Okay, so just because there's an exponent doesn't mean that we're not still multiplying. I squared means I times I by definition. Okay, so we are multiplying, and the rule is when you multiply or divide, you add the percent uncertainties. So that means we would add the percent uncertainty in I, which is 2%, that's given, plus the percent uncertainty in I, which is 2%, plus the percent uncertainty in R, which is 10%. And that would give you a grand total of 14%. Okay, so pause there if you need to look at that some more. Okay. Let's do another example. Okay, it says when a force F of 10 plus or minus 0.2 newtons is applied to a mass m of 2 plus or minus 0.1 kilograms, the percentage uncertainty attached to the value of the calculated acceleration F divided by m is what? Okay, so in other words, they give you F and they give you m, and they're asking you what would the percent uncertainty in F divided by m be? Okay, so obviously we have an equation. Oops. The equation is that they're telling us that the calculated acceleration, which by the way, you probably have no clue what this is, or maybe you do, but it doesn't really matter for the purpose of this question. Okay, so the question is asking what is the percent uncertainty in F divided by m. So pause it here and see if you can figure this out on your own. Okay, so before I do this correctly, let me tell you what not to do. Here's what you should not do. Okay, what you should not do is say, okay, F over m is 10 over 2. Okay, so that's 5. And then it would be plus or minus 0.2 plus 0.1, which is 0.3 newtons. And then I need to convert that to percent uncertainty. Okay, that would be 5 plus or minus 0.3. And then that would be 5 plus or minus 6%. That would be absolutely not correct. Okay, do not do that. That is not following the uncertainty calculation guidelines. That is not what you should do. Okay, here is the correct way to do this. If you follow the uncertainty calculation guidelines, what you should do is, hey, I'm dividing, and the rule says that when you multiply or divide, you add the percent uncertainties. The problem is that we do not have the percent uncertainty in F or the percent uncertainty in F. Okay, so even though we can divide the values, we cannot deal with the uncertainties until we convert both of these to percent uncertainty. Okay, so F would be 10 plus or minus 0.2 over 10 times 100. Okay, so that would be 10.0 plus or minus 2%. And then M, again, we're converting to percent uncertainty. And the thing that tells us to do that is the fact that, hey, we're dividing. And the rule says that when you multiply or divide, you add the percent uncertainty. Okay, I always have people ask me every year, like, how do you know you need to convert to percent uncertainty? It all comes down to the operation. Okay, every problem you do is going to have some type of mathematical operation, either adding, dividing, subtracting, multiplying, whatever. Okay, the operation that is division tells me that I need to add percent uncertainties. Since I don't have percent uncertainties, that tells me I need to find them. Okay, so it all comes down to the operation in the problem. All right, so that means the acceleration would have an uncertainty of the percent uncertainty in F, which is 2, plus the percent uncertainty in the mass, which is 5. And so 2 plus 5 equals 7%, and the answer would be C. Okay. Pause there if you need to wrap your head around that some more. All right. Okay, just a few more examples. Let's see if you can do this on your own. The radius of a loop is measured to be 10.0 plus or minus 0.5 centimeters. Which of the following is the best estimate of the uncertainty in the calculated area of the loop? And in case you don't know for some reason, the area of a circle is pi r squared, and I will give you a big ol' hint that pi has no uncertainty because it's not a measured value, it's a constant. Okay, so let's see if you can figure out this on your own. Pause it there and try to answer this question. Okay, so the correct answer is C. in the interest of time, I'm not going to go over the whole thing. Okay, but hopefully if you got C, that's good, and if not, then please come ask me for help if you can't figure it out on your own. Okay, so the answer there should be C. Okay, and then the final question, it says the current I through a resistor is measured with a digital ammeter to be 0.10 amps. The uncertainty of the calculated value of I squared will be what? Okay, now if you're not paying close attention, you might say, oh, wait, they don't give us the uncertainty. How are we supposed to do this? Okay, well, read the question carefully is all I'm going to say. Okay, so pause it there and see if you can figure out the answer to this on your own. Okay, so the correct answer to this question is D. Remember, a digital measuring device, this is a digital ammeter. Okay, a digital measuring device has an uncertainty of plus or minus 1 in the last decimal place. And so the uncertainty is taken to be plus or minus 0.01. And if you convert that to percent uncertainty, you get 10%. I squared, okay, means that you're multiplying, and so you need to add the percent uncertainty in I plus the percent uncertainty in I. That would be 10 plus 10, which is 20%. Okay, so that is how you do uncertainty calculations. I will leave the video here, okay, because it all comes down to understanding these guidelines. You should be able to do all of your practice assignments now. Please, please, please let me know if you have any questions with any of those assignments. If you can handle these uncertainty calculations, then you should be perfectly fine for the test. Okay, again, this is the last video for this unit. Okay, please let me know if you have any questions, and as always, I will see you guys in the next video.